Okay, good afternoon. Thank you for having me here. And today I'm going to talk about the DOM-POM continuum. So before I move into there, and I am going to talk about a little bit about the importance of microgels. Microgels are three-dimensional networks that are formed and link biology and microbial processes at the ocean surface with biogeochemistry in the deep ocean. And they form hotspots in the microbial loop, and important in the microbial loop. And they assemble at the interface between the ocean and the atmosphere interaction. And they can also be important and form cloud condensation nuclei. So they affect, in that sense, climate. So as you see, microgels can be important in all these processes. And especially today, we want to understand how they can be important in the DOM-POM continuum in the ocean. So the dissolved-particulate continuum refers to the processes that transform DOC polymers that are in the nanometer size range into nanogel-sized particles that anneal into forming bigger size microgels and even macrogels of bigger size. While most of the work has been done in macrogels, DEP and EP and marine snow, and looking and searching at Google, there you can see that there's more than 1,000 papers in that area, but almost very few in this range in the dissolved to particulate. So in this case, it's very important to understand what are the rates by which DOC polymers are transformed into microgels, nanogels, and nanogels. What are the pools of these three components? So, but before I go into that, we need to understand what are gels. Why do we talk about gels and not particles? Gels are a very special form of soft matter. They are networks, three-dimensional networks, composed by a polymer net and a solvent. And the characteristics of the polymers, length, flexibility, their electrolytic properties, the degree of hydrophobicity, the donor properties of the polymers, and the volume of the solvent, the viscosity, ionic strength, pH, etc., allows these networks to entrap the solvent, but the solvent at the same time prevents the network to collapse into each other. And so this interaction between the polymer network and the solvent determines the behavior of this network. This is very important because this behavior brings together emergent properties that are very different from the properties of the polymers itself. So these characteristics make gels, their structure is very extraordinary in the sense that are very flexible and with a gel-like soft matter material, and they form the basis of most of the modern chemistry and that has advanced to produce our contact lenses, to diapers, to many of these products, drug delivery that is also based on polymer physics, that takes advantage of all the characteristics of these networks. So this dissolved organic matter accounts for that accounts for 662 petagrams of carbon. Is an enormous pool with a very complex chemical polymer material that goes from carbohydrates, proteins, lipids, nucleic acids. All these polymers can assemble together into forming gels that are cross-linked by calcium ions. Although the community has learned tremendously about the chemistry, about this pool of polymers, we still know very little. And we still have a lot of unknowns about the sources, the sinks, and the dynamics, and especially the role of polymers in this in the DOM. So we all know that a high percentage of the primary production is released as DOM. Between 20 and 50 or 80% depends what you read. So the processes of production vary from extracellular release, bacterial lysis, regulated exocytosis, apoptosis and programmed cell death, grazing, and dissolution of large particles. So I cannot give the references of everybody, but it's fair to say that many, many people have worked in understanding these processes, and here are some. And as Pierre Durand says, he has a very beautiful paper in natural ecology, and he says that the way you die affects your fate. So yes, it's different to be dying by a programmed cell death than a viral lysis, because the particles and the polymers that you might produce are going to be different. So can we predict this polymer production? Well, not yet, but we are going in that direction. So this cartoon shows the different physiological and transcriptomic states of the model diatom Thalassocyra pseudonana. And now systems approaches and high-throughput measurements such as genomics and metabolomics and transcriptomes allow us to be able to have detailed knowledge of the physiological and transcriptomics of these cells. And we are then being able to know when the cells are going to produce polymers, under what conditions. In here, these four states, day and night, with nitrogens and limiting nitrogens. Well, the most important part of this is that it allows us to understand the regulation of gene expression. That this is an inferred gene regulatory relationship for Thalassocyra pseudonana. And all what I want to say is that the more we learn about this, the more we understand about when, how, and under what conditions the cells are going to produce polymers, the ones we are interested in. So also, knowing this for several cells, several kinds of cells, allows us to understand and interpret why and the different kinds of cells, bigger cells, can produce polymers that assemble into macrogels, and cells that only produce microgels. So here, an easy example that we know the macrogels or TP or are going to be exported immediately, very fast in the water column. But these gels are going to stay there. However, they have emergent properties that allow them to assemble and form bigger sized gels. So how does this happen? So this is a paper, somewhat old, but it's important for this talk today. So in 1998, Shin et al. Demonstrated that free polymers can assemble into forming gels. This process has a second-order kinetics. That means that it's a two-step-wise process in which the polymers first come together at a few hours, and after that, these small-sized nanogels are going to interpenetrate, the polymers reptate and interpenetrate each other to assemble into bigger sized gels. These plateaus at around 5 microns. Of course, this is in a tube, but in the ocean, where they have an infinite amount of polymers, this process can continue. So these rates and kinetics are mostly unknown for all over the ocean. In this example, they chelated the seawater also with ETDA. So chelating the calcium, that meant that the assembly process was dependent on the amount of calcium present, and that the polymers were linked together with calcium ionic bonds. That you can see in the inset X-ray dispersion analysis showed that the major peak of the metal ion is calcium. While other metals also could do, like magnesium is also important in the ocean. Magnesium has a very big Debye field. Instead, calcium has a smaller one. So the polymers that are in the ocean that are mostly polyanionic, cross-linked by calcium. So in order to also completely demonstrate that this process was a two-step-wise, they imaged with atomic force microscopy free polymers, fibril polymers, that assembly into forming nanogels. In this case, there are three coming together, interpenetrating and annealing. And then at 60 hours or so, they form a bigger microgel. As you see, this microgel is formed by many small size nanogels. So this process is reversible, and in the case of these gels, the thermodynamic yield is of 10%. So we now know and have found in the ocean that in certain areas, after blooms, this yield can be 30%. And now just came another paper out in which these yields varied from region to region. So the composition also with, just to show that these gels, the chemical composition of these gels is similar to the bulk composition of the seawater. They use stains, chlorotetracycline that stains for bound calcium, Nile red for hydrophobic moieties, RuBisCO for proteins, and DAPI for nucleic acids. So this meant that, of course, that the gels were forming by a poly-dispersed and from polymers from the ocean directly. So, so what do we now know also that these kinetics of assembly can be different and not always be a second order kinetics. Before I showed you polyionics polymers assembled together with calcium ionic bonds. But in this case, the kinetics of assemblies is very, very, very fast. In a few hours, the gels reach plateau. In this case, although they can be stained by chlorotetracycline, showing that they do have calcium, they do also have hydrophobic pockets of, with the presence of hydrophobic amino acids. These amino acids form pockets that allow the assembly to go faster. So in the top photo images are gels that show in red the hydrophobic portion of the gels, and in green with quinacridine, the hydrophilic portion of the gels. And in the lower panel, the enrichment of amino acids in the microlayer that corresponds with the amino acids that we found in the microgels. So now we understand that the hydrophobic, having hydrophobic or at least a certain amount of hydrophobic moieties increases the rate of the assembly, but increases and also can change the size of the polymer size of equilibrium. So in this case, the top these are hydrophobic moieties in Emiliana Huxley, and Ding et al. Showed that they can assemble in artificial seawater, but they can also assemble in artificial calcium-free seawater, showing that only by the presence of the hydrophobic moieties they can reach this assembly process and form particles. So all these, this one at least, it's in the laboratory. However, these assembly processes can be affected by the synergistic effect of pH and temperature. So it's not so easy to go and measure the rates of assembly. For example, in this case, temperature and at high temperature and higher pHs, there's an inhibition of the assembly. And this inhibition lowers to 28 degrees when the pH are lower at 7.3 and 7.5. So this is not so easy in the sense that not every pattern fits all. Now, so what happens with the polymer size? I said at the beginning that the length of the polymer was also important for the understanding the gels. Polymer theory says that the assembly process is proportional to the square of the size of the polymers. So when you have long polymers, like those that come out after a bloom, immediately after a bloom, they assemble, in this case, in a second order kinetic fashion, and the stability of those gels is attained at like 5 microns. However, if these gels are irradiated and the polymers are photocleaved, after 30 minutes of irradiation and then start the assembly, you can see that the assembly process only reaches gels a lot smaller than at the first non-irradiated. And if you continue 6 hours and 12 hours, you can see that the assembly of microgels, these microgels are smaller and smaller. So what is happening? The polymers are getting shorter and shorter, and the stability of those gels is getting less and less stronger. And that's because the interactions between the polymers itself, the tangles and the interpenetration is getting weaker and weaker as the polymers are smaller. So, and what about the 24 hours? This is very interesting and has very many implications. For example, at 24 hours, you see, we are talking of very short polymers, and they don't assemble, or if they assemble, the polymer gels are very, very unstable. And this is because, as I just said, there's no, the tangles and the interpenetrations of the polymers itself are very weak, and the electrostatic interactions are very weak. So this also tells us that it may explain why the majority of the polymers in the ocean are very short size, are very small, and very old. This might explain why very small polymers accumulate in the ocean because they cannot assemble. So the majority of the polymeric material in the ocean is long-lived and short size. So other processes also fragment polymers. And you all, oh, before I was skipping something. I also wanted to show you that in this process, the polymers, the microgels decrease exponentially in size. The polymers decrease exponentially in size, as well as the microgels. And so in this case, the microgels that I showed you at the beginning, as one microgel with smaller microgels interpenetrating, they disperse because now the polymers are so short that they disperse and into the water column. So other processes also fragment polymers. And in this case, these are polymers fragmented by bacterial degradation. As degradation increases, polymers get smaller and smaller and smaller. And so the interpenetration, the tangles, and the ionic interactions between the polymers is weaker and weaker. And at the end, we also have very short polymers. So in this case, theory of polymer physics is really showing us what we see in the ocean and implying that we can explain this DOM-POM continuum by applying theory and tools, mathematical tools of polymer physics. So there's another important emergent property that gels undergo, and this is volume phase transition. Volume phase transition is the process by which swollen gels can abruptly undergo a transition and become condensed and a rock-like network. This is important because microgels that we thought that maybe couldn't be exported in the water column, if they are as a dense, if they are formed by a dense network, they have a high density and they can sink very fast. This process happens very fast and happens under different environmental conditions, light, heat, ions, pollutants, electric field, etc. This cartoon is for, of course, for artificial polymers. However, it also happens in the ocean. Temperature, for example, that I'm not showing, but also polymers can undergo, under certain conditions, polymer phase transition. In this case, I'm going to show in the top panel, in the top panel, I want to show the phase transition of the microgels that is produced by when they are in a low quantity of sulfuric acid. The sulfuric acid should be up there. I don't know in what minute it moves. In any case, as you see, the gels, the microgels change size and also a number of that we could count from pH 8 to 6 in a very fast way, and then they are very, very tiny, and we cannot count all of them. So what happens here is that when they are swollen, they are, of course, very big, but under H2SO4, that is the composition of the MS in the clouds, this shrinks, and in that case, maybe these gels can be cloud condensation nuclei. The same happens with the effect of the MSP and the MS. So maybe this is more closer to us in the water column. These are gels in the top panel composed of RuBisCO, the enzyme that fixes CO2 in the water, fixes CO2 during photosynthesis. RuBisCO microgels undergo phase transition at pH 7. And this is very important because RuBisCO is a soluble protein inside the chloroplast. And as a soluble protein, you would imagine that it would be degraded fairly fast in the water column. However, the fact that they transform into a rock-like network, it may increase the probability that we can measure RuBisCO in the water column. And that's how we can explain RuBisCO in the deep Pacific Ocean. This is a transect at P16, the Kleiber line P16. And what you see here is the export at the fronts in the equatorial Pacific and in the subarctic zone in Alaska. Those are at the fronts are the regions where RuBisCO is exported. But also you can see advection taken from the deep Pacific current into, as it comes up to the surface, it's advected to the south. In the gyres, the concentrations are lower. But what this is saying is that our capacity to measure RuBisCO at 4,000 meters is we explain by the fact that RuBisCO is not degraded. and is not degraded because probably undergoes phase transition inside the guts of microzooplankton or vacuoles or of protozoa. So understanding these effects and the emergent properties of microgels applied to problematics in the ocean and trying to understand these distributions is very important. To finalize, I want to show you microgels that are also found in clouds and aerosol fogs and aerosol particles. These are microgels coming from polymers from Melocera arctica that was forming a bloom in the ocean when we were in the Arctic. These microgels have a high percentage of hydrophobic moieties and are important in cloud formation. So what is important about microgels is that they have a non-Newtonian rheology and a porous structure. This is different from colloids, like gold colloids. They might have colloidal size, but their characteristics give them properties that are completely different from the polymers that form them. And these characteristics also define their kinetics, their assembly and dispersion, their swelling, their phase transition, and something that I didn't talk, their Donan characteristics. Just to let you know, Donan is the capacity of trapping ions, and that's important as well because theory of polymer physics also shows that the capacity to trap ions is related to the square of the valence of those metals. So for example, in iron and aluminum with a valence of 3, the capacity to get and sequester those ions is very high. So like, for example, siderophores that have this capacity. So, polymer, soft polymer theory applied to understanding DOM-POM continuum is very powerful because with those few examples that I gave you, it allows us to understand how or when, under what conditions, gels are going to assemble, gels are going to undergo phase transition, and are going to determine if the gels are going to assemble and go into the POM, and with having a high biological and chemical bioreactivity, or also understand how degradation and the rates of degradation, chemical or UV, are going to produce very short polymers that do not assemble. So I think that soft matter physics has a very strong theory and an enormous case or tools, mathematical tools, to model all these processes, and can help us as a community to understand the DOM-POM continuum. So with that, I want to thank you all for listening, and that's it.